This is part of Signals and Systems video series. We're going to talk about convergence, specifically as it relates to Fourier Series, continuous time Fourier Series. The basic idea of convergence is that if we have a Fourier series in this particular case, and as it's represented, this is a Fourier series approximation. If n was infinite, in this case, this summation would give us exactly x of t. So the error, the difference between the actual x of t and the approximation that comes from the Fourier series summation would be 0. But since we cannot go into the infinite, we approximated but as n increases, we should see that error get smaller and smaller. In some cases, that is not exactly what happens. If the system is convergent, as n grows to the infinity, we would get error going to the 0 as is shown here. So for a convergent signal, we will have a valid Fourier series, and as n goes toward the infinity, the result, the e of n, this quantity, which is the difference between the actual, this would be the actual value of x of t, and this would be the estimate based on Fourier series, should be equal to each other, therefore it ends up being equal to 0. Or another way it's put in here, x of n of t, the approximation, would be going closer to x of t with every additional n. As n increase for every step, we get closer and closer. If the signal is non-convergent, that doesn't happen. Therefore, our estimates based on the Fourier series does not get closer and closer to the actual signal, which means the Fourier series is not valid, even if we are able to calculate it. So how do we know if our signal is convergent or not convergent? And the way we look at it, we basically say signal does not converge if either of these conditions are true. If a of k, as we calculated, does not converge. In other words, as we increase our a of k, it doesn't get the difference doesn't become smaller and smaller. And then at times a of k converged, but some does not converge. So in other words, we have cases where a of k converges, but the summation does not converge. And as you can see, I have to take every signal and run it through this integration and through this summation for multiple cases of k to prove that that situation exists. And this is very difficult to do in actuality. So if a while ago, there was a fellow by the name of Dirichlet who came up with the 3 conditions for convergence, which are really easy to test. And not only they're easy to test, but they also tell us something really important. And the punchline is that there aren't too many signals that we care about that are non-convergent. In other words, that's really good news. That means majority of the signals we are interested in are convergent, and we can find Fourier series for them. So let's take a look at the 3 conditions that Dirichlet came up with and see if they make sense. They're very straightforward, very easy to understand. One says that condition 1 that has to be true basically says x of t must be absolutely integratable. And the basic idea is that if I take a summation of x of t, any interval t, it should be less than infinite. So here is an example of one that is not, for example, and it's going to be, we don't have too many signals that look like that. And as you can see here, we have a couple examples of signal that potentially would exhibit this behavior. Condition 2 basically says that if any finite interval, any finite interval I can pick, x of t has finite variation. In other words, it can't keep bouncing up and down all the time. And an example of this would be some equation as is shown here. And again, it's not the very common and everyday signal that we're looking at. Condition 3, it's even less rare in some ways, and that basically says in any finite space from, let's say, 0 to minus a or 0 to a, just pick a for whatever you want it to be, we will have finite number of discontinuity So we can count it basically, how many discontinued. It doesn't mean we don't have lots of discontinued. It just means it is countable and we have a number we can attach to it. That's the same thing with the oscillation. You can have lots of oscillation, but as long as you can count it and come up with the number, we're good. And so both of these are kind of the variation on the same theme. And if condition 3 is true, where there's finite number of discontinuity, then we can say that this signal is good, and we can go ahead and use the Fourier series for this signal. So once again, these Dirichlet conditions are a quick way of figuring out whether our signal is convergent or not, without having to go through the rigorous exercise of looking at these integrals and summation to figure it out. Okay, so that brings us to the end of this quick talk about, or video about, convergence of continuous time Fourier series as part of the Signals and Systems series.